Okay, so good morning everyone. I'm going to give you a brief talk today about some facets of the work I've been doing during my PhD here in Cambridge. And this is mainly with input from John Hinch, but with the occasional bits and pieces from Jim McElwain. So the problem I was initially interested in was what I like to describe as at dinner parties is how to not make a sandcastle very well. In other words, the column collapse problem. Very simply, take a column of grains in a cylinder, whip the cylinder away, and then the material spreads out. This has some fairly obvious geophysical application, which has been mentioned already in parts, among others, by Bruce yesterday. And in terms of the geophysical hazard, what you care about is how far this material is going to spread as a function of the initial geometry. Now, there's been a wealth of experimental data in this area where they can show that given, well, the only important parameter is the initial aspect ratio of the column, and it turns out that from that,
flick the switch.
oh, so the only important parameter is the initial aspect ratio of the column, and from that you can get power laws for the duration of the event, the total run-out distance, how far this thing spreads. And you'd think, given that was such a simple relationship, that some theory would be able to get a long way with that. Sadly, so far, nobody's really nailed it. And that's possibly because most of the efforts so far have been in shallow water models, which, sorry, is it all right? Okay, you're just looking confused. Which of course reduce the dimension of the model. So what we'd like to do to maybe get further is to go away and come up with a proper, either two-dimensional in a 2D collapse or three-dimensional in a proper column collapse, try to come up with a proper continuum model. And of course to do that, we need a constitutive law. Now, with some degree of trepidation, I can see Charlie's looking at me now, so I'm going to be careful here. You'll notice this is now an inertial number, this dimensional relationship verified by the JDI MIDI. I'm not going to say it's first proposed by or anything like that. But the point is we have this local parameter, this local dimensional parameter, which is called I, which you can think of as a ratio of two timescales, like every other dimensional parameter, I suppose, dimensional parameter. And the important thing is Olivier's contribution was to propose this tensorial constitutive law, which says that your shear stress is linearly related to your pressure, your normal stress, and the constant proportionality here is just this friction coefficient mu of I, which has this sort of form down here. There's three fit parameters here, mu1, mu2, and I0, which you can get from very simple experiments. And to make it properly 3D, we need a direction, and that direction comes from the direction of the rate of strain tensor. And using that, we've already seen in a number of talks so far. In fact, I think Olivier had pretty much the same slide, just oriented differently yesterday. Two flows where it works very well. Here's flow on a deep pile of sand, in which case you can get a very good prediction of the surface velocity profiles. And it can do a stability analysis and get the stability criteria for roll waves on an inclined plane. And that also matches quite well. Incidentally, this is the red line matching the data quite well from this mu of I law. The dotted line up here is one of the best efforts of a shallow water model. So perhaps there's some good reason to be considering this proper 2D approach. So a new result, which is actually sort of treading on Tamas's toes for 2 talks' time, he's been looking in a bit more detail at these longitudinal vortices you get if you have a dense inclined flow. So this is not roll waves anymore. This is now, if you're looking down the flow, you get vortices spiraling round in the direction of the flow. And you can see these stripes forming if you look at the surface of the pile there. And it turns out, if you go away and use just this very simple local rheology, then you can predict this instability just using linear stability analysis. To get rid of roll waves, we don't worry about any variation down the slope. We just have a cross-slope wave number, which we call little l. And here we are. We've got, for example, a plot of the stability diagram. We've got the Froude number, which is really just a proxy for the depth of the flow. And plotted against this wave number, we can see there's an unstable region, a stable region. And the stable region gets a bit bigger as you increase the angle, but that's a detail that isn't really very important. So what's my point? My point is that oh, yes, I forgot about this one. So this is just something you should bear in mind for 2 talks' time. This is what the structure of the perturbation to the solution looks like at the onset of this instability. What's important is that here we have a cross-section through the flow. The colors show you the perturbation to the downslope, the mean flow. So you can see you get regions where it's faster, regions where it's slower. And there's also, if you squint, you can see the arrows. I couldn't make them any bigger, I'm afraid. You can see there's a rotation in this sense, so it's coming down there's a downwelling where the flow is faster. So what am I getting at with all this? I'm getting at the fact that this simple constitutive law, despite the fact we've all been talking a lot today about why things should be more complicated and we should worry about a lot of different physical effects, I claim that this simple law can actually do quite well in a bunch of free surface cases. So what does this mean for a column collapse? Well, another thing that would have been mentioned earlier in the week, had Laurent Lacaze been here, he would have talked about his DEM simulations of the column collapse and how they match very well to, if you look at coarse graining out the shear stress of the normal stress, you can get a decent match to this mu of I relationship with the same sort of values for these parameters as we're seeing in the simpler cases we saw previously. So what we've been doing with that most recently is actually trying to come up with a solver for this done properly. So at the moment it's not done properly, unfortunately. But this is what we have so far. Just to show you what we have just a simple Lagrangian finite element scheme which is collapsing reasonably. You'll notice I say reasonably because it's still moving at this point. Notice down here it doesn't move very much, but it still moves. And then after it's more or less stopped, there's still a gradual spreading. Now that is because we've cheated, and I think it was Julien on Monday who mentioned that you can regularize the viscosity. You need to get this, what happens when you have a zero strain rate. Well, we regularize it by putting some little positive number in there. Although, of course, in the real problem, we need to worry about the plasticity properly. Another good reason why we want to worry about plasticity is if you look a bit more carefully at these collapse flows. This is now a DEM simulation did by Lily Staron and John Hinch a few years ago. And the idea here is it's exactly the same problem. You've got a column collapsing, and if grains move, they color them black, and then they stay black for the remainder of the flow. And the important thing to note is at the end, you get this nice static wedge, which never moved at any point during the collapse. Now, curiously, the shallow water models, if you apply them to something on this sort of topography, where you start with a static wedge and you say, well, let's have a shallow water flow over that, then that actually works quite well at predicting the runout, and that was done by Emma Doyle in Bristol. But of course, that's only if you know a priori the location of this static wedge, which is non-trivial. So what we'd like to be able to do, in another sense, is to work out where this transition between the static and the flowing regions are, and just by means of a very, very simple example. This is just a simple linear shear, but there's a twist. We've added in some gravity just to create a pressure gradient. So this is more or less analogous to an annular Couette flow. And all I'm trying to show with this slide really is that we can use this mu of I rheology, and we can get a perfectly good solution out of here, which has a finite shear band, so there's no motion at all down here in the velocity. And the width of the shear band, which I call delta, varies with the rate at which you pull this, this top plate. And the point is, it saturates at about 3 grain diameters, which is perhaps a little on the small side. And indeed, this is one of the criticisms of this, this mu of I rheology, and the predicted shear bands are maybe a little bit too small. However, it's interesting to note that at least qualitatively, this sort of shape agrees with some now quite old MD simulations, which came out of Thompson and Grest's work in the early 90s. And this is essentially modeling exactly the same problem. The only reason why we get 2 different curves here is because they're 2 different sets of microscopic parameters, and we're plotting the shear stress against velocity rather than the shear band thickness against velocity, but these 2 things are linearly related. Right, so that's in 1D, we can get at what these shear zones look like. In 2D, you have to do a bit more work, and indeed, you have to come up with some sort of heuristic way of determining, at least in a numerical sense, where the boundaries of these shearing regions are. So all I'm trying to do with this slide is give you a picture of 2 flows. One where we've got the exact same flow, we have a confining pressure and then a plate that's being pulled along, but then we split it so we've only got a slice of that plate being pulled, and we can get flows that look like that, and there's some details over the how we get the boundary between flowing and not flowing. And also, something I believe we might be getting a talk about tomorrow, which is this split bottom Couette shell, where you have 2 L-shaped walls which slide past each other. And in that case, again, you can get some idea numerically of what this, what the shape of this shearing region might be. And this is all just coming out of mu I with some empirical, well, not empirical, some sort of heuristic cheating, for want of a better word. Right, at that point, I'll wrap it up. All I'm trying to say with this talk really is that this simple mu of I law, it does all right. It's quite good at doing a lot of things with free surface flows, as I've shown with some previous results, and then this new result about the longitudinal vortices. And the column collapse, I think, is now very much in sight. We've got all this information saying that the stresses are about the right sort of fit to this law, and it's just a question of getting this code to work properly, which is surely only a matter of time, I hope. So with that, I'll say thank you very much for your attention. And
Questions? I have one about the instability, the longitudinal instability. That's without any volume fraction.
so
variation.
all this is completely incompressible. There's no
So you
dilation.
understand? You have some arm waving argument within this framework about original instability.
We've thought quite hard about how we can, what sort of physical mechanisms going on
Yeah.
here, and we haven't come up with a good one yet. If anybody has any ideas, I'd love to hear them, but I think Jim and I have spent a while thinking about it and just got nowhere. So.
Yeah. Alright.
Does du of I go to 0 anywhere as I goes to 0 in the simulation?
So, sorry, the mu is bounded between two strictly positive limits.
Yeah,
So
sure.
you go to a positive friction coefficient, so
No.
it doesn't go to 0.
No, does it approach 0?
The friction coefficient mu, no, there's a finite yield stress in there.
No, in the results you got from the simulation.
Yes. Sorry, what you're asking if the friction coefficient itself goes to 0?
Yeah.
Then I say again, the friction coefficient is bounded below by this mu1, and that's what's going into simulations. Are you saying about the DEM simulations?
Yeah.
Okay. So I think I'm not an expert on the DEM. I must admit it's not mine. It's other people's work. So I think from looking at the preprint from Laurent Lacaze, when he makes this plot, he doesn't worry about. There are some reasons that he discounts when he plots that relationship. So there's some where it's free fall,
Okay.
essentially got no friction. So yes, in that case there are some places. Sorry.
So I have a question. In your DM simulation, did you consider the volume fraction? In my experience, if there are no volume fraction, maybe the angle, the angle of the repulsion maybe will be harder. I mean, difficult to form an angle. For a very long time, I think the particle will become light. So how to consider this?
So just to make sure I understand, the question is.
I mean, in your DM simulation,
Mhm.
I mean, did you consider volume fraction?
No, so, well, I mean, in the DEM, obviously, the particles go where they go, and there'll be some expansion in there. But the objective, what I've been doing, which is based on this continuum model, at the moment, I've just completely tossed out dilation, because the argument goes, let's make it as simple as possible to see if it works. And hopefully with that thing about the instability, you can get quite non-trivial physical effects without needing to worry about dilation. I mean, sure, with that instability, the nonlinear development might be different, but at least it's getting the instability right, so maybe we don't need to worry about that too much right now, is the hope. Sure, there are details, but we need to worry about details later.